Different languages provide different patterns for implementing opacity effectively. Let me walk you through several approaches. In Java, the interface plus factory patterns work well. You define a money interface that specifies the operations but not the representation. The There's a money factory here which provides static methods to create instances. And the money impl class is package private, so clients cannot access it directly. This pattern gives you complete control over construction and ensures that clients can only interact with the money interface. You cannot you can change the internal implementation of money impl without affecting any client code. Now, in TypeScript, closure modules provide excellent opacity. You define a function that creates and returns an object with specific methods. But the internal state is captured in the closure and completely inaccessible from outside. For example, a create secure token function might capture a hashed value and attempt counter in its closure. The returned object provides verify and is logged methods, but clients have no way to access the internal hashed value or the attempts variables. In Rust, the new type pattern combines with module privacy, provides strong opacity guarantees. You define a struct that wraps a primitive type, but the inner field is private. You provide associated functions for construction and methods for operations. For instance, a user ID struct might wrap a U64, but clients cannot construct invalid user IDs or access the inner value directly. The new function validates input, and other methods provide safe operations on the ID. Each of these patterns achieves the same goal through different language mechanisms, making the representation unknowable to clients while fetching a rich behavioral interface. Now, let me give you a practical checklist for evaluating whether your modules achieve representational independence. First, ask yourself, does the module expose raw data? If so, what raw data leaks freeze the representation and make future changes difficult? Second, does each public method express intent rather than structure? Methods that expose structural details violate independence, while methods that express business intent survive redesigns. Third, can the abstraction function and representation invariant be stated cleanly? If not, the abstraction is probably muddled and needs clarification. Fourth, do tests observe behavior only? Tests that make structural assertions violate independence and will break when you change the representation. Fifth, can you swap the representation tomorrow? This is the ultimate litmus test for success. I call this last point the swap test. Ask yourself, if I need to completely change how this data is stored internally, how many files would I need to modify? The good answer is just the implementation file. The bad answer is dozens of files across multiple packages. If changing your internal representation requires touching lots of other code, you don't have representational independence yet. Now, let me show you another detailed example of transforming transparent data into opaque value objects. This example involves financial data where the stakes for getting it right are particularly high. The initial design uses a transparent struct. The ledger entry class exposes the account ID as a raw string, the amount as a raw big decimal, the memo as a raw string, and the creation time as a raw timestamp. Now, the clients become coupled to this representation in predictable ways. They negate amounts by calling negate directly on the big decimal. They create display strings by concatenating dollar signs with the toString method. They determine if an entry is a debit by comparing the big decimal to 0. And they build JSON by depending on the exact field structure. The pain points become apparent when requirements change. Multiple currencies aren't supported because everything assumes a single big decimal. Rounding errors break ORM mappings because precision isn't controlled. Memos need localization, but there's no structure for it. Account ID validation is scattered everywhere because there's no central place to enforce rules. Audit trail requirements can't be added without changing every client. The refactored design uses opaque value objects throughout. The ledger entity class now has an account ID, a money object, a memo object, and an audit trail object. The constructor is package private, forcing clients to use the factory methods. The factory methods control construction and enforce business rules. There's a debit method that creates a debit entry by negating the amount. There's a credit method that creates the credit entry with a positive amount. Both methods automatically create audit trails. The behavioral interface expresses domain types clearly. The isDebit method encapsulates the logic for determining entry type. The display amount method handles currency formatting properly. The FX account method provides a clean way to check account relationships. The add memo method creates a new entry with additional memo information and proper authorship tracking. Now, each supporting type is also opaque. Account ID encapsulates validation and formatting rules. Money handles currency conversion, rounding, and formatting. Memo manages localization, versioning, and authorship. Clients now work with domain concepts rather than implementation details. They create debits and credits using the factory methods. They get formatted amounts using the display amount method. They check entry types using the isDebit method. The outcome of this refactoring was remarkable. Switching from decimal to integer minor unit storage, storing cents instead of dollars required changes in exactly one file. Adding multi-currency support requires changing one file. Adding audit trail requires changes in one file. This is the power of representation independence applied systematically throughout a domain model. Let me warn you about several common mistakes that can undermine representational independence. The first pitfall is providing helpful getters. You might think that exposing raw data is just for tests is harmless, but it breaks opacity just as effectively as public fields. Instead, provide test helpers within the module that construct objects in useful ways for testing. The second pitfall is using stringly type fields where every caller has to re-implement parsing logic. If you store a date as a string with a hidden format, clients have to parse it themselves, which couples them to the format. Use domain types with clear interfaces instead. The third pitfall involves leaky DTOs for serialization. If you serialize the internal structure directly, you are exposing the representation through the wire format. Instead, create dedicated transfer objects that represent the data in a format suitable for external consumption while hiding internal implementation details. The last pitfall involves exposed collections. If you return mutable internal state directly, clients can modify it, which violates encapsulation. Return immutable views or streams instead. Each of these pitfalls seems minor in isolation, but they accumulate to destroy representational independence and make your code fragile in the face of change. Let me summarize the key principles that will help you achieve representational independence consistently. The mind shift is crucial. Stop thinking about exposing fields for convenience. Start thinking about the smallest behavioral interface that serves client needs. Ask yourself what clients are trying to accomplish, not what data they need to see. Focus on expressing intent through method names and signatures. Instead of exposing a year field, provide a is published before method, for example. Instead of exposing an author field, provide a compare by author method. Use the abstraction function and representation invariant as design tools. If you can't state them clearly, your abstraction probably needs work. Design for change from the beginning. Assume that your internal representation will evolve and make sure clients can't depend on it. Test behaviors, not structure. Write tests that verify what your module does, not how it does it. Now, the most important ideas from this lesson: representation independence will free you to evolve internal code without breaking collars. This is perhaps the most powerful tool you have for managing complexity in large systems. Opaque data types enforce that independence by making representations unknowing. The language mechanisms vary, but the goal is always the same: prevent clients from depending on internal structures. Abstraction functions and representation invariants are the formal backbone that keep abstractions honest. They help you reason about correctness and maintain invariance across changes. Secrets are your safety net. They enable change without cascading edits throughout your code base. The more secrets you can keep, the more flexible your system becomes. The business impact of these principles is significant. You get faster feature development because internal changes don't require client updates. You get safer refactoring because representation changes can't break anything. You get better testing because you focus on behavior rather than implementation detail. You get easier maintenance because changes are localized to single modules. Remember this principle: design modules so that behavior is public, state is private, and change is cheap. This is the essence of representational independence, and it's one of the most valuable skills you can develop as a software designer. When you master these concepts, you'll find that your code becomes more robust, more maintainable, and more adaptable to changing requirements. You'll be able to evolve systems with confidence, knowing that your careful attention to abstraction boundaries protects you from the coupling cascade that destroys so many software projects. This concludes our lesson on representational independence. The principles we've covered today will serve you well throughout your career as you build systems that need to grow and change over time.